When scientists of the 17th and 18th centuries were studying historical records of eclipses, including information dating back thousands of years, which became accessible thanks to astronomers at the Chinese imperial court, they noticed an intriguing pattern. Their calculations and observations didn't align with the ancient sages' records. The calculated dates of ancient eclipses didn't match up with historical chronicles. As they delved deeper into the past, the discrepancies became more significant, and the intervals between eclipses grew longer. This discrepancy became evident when examining the history of these phenomena over thousands of years. What was happening was that the rotation of the Earth was slowing down. Perhaps the Moon was moving away. It would take future generations of astronomers and physicists to piece together this puzzle and discover that the Earth's rotation was indeed slowing down, and the Moon was gradually moving away. But what connects these processes? Let's find out together. But first, let's recall what we know about the Moon. The Moon is Earth's only natural satellite. According to the most popular theory among scientists, sometime after the Earth's formation, a celestial body the size of a planet collided with it at a tangent. As a result of this impact, some of the material from this object and part of the Earth's mantle were ejected into orbit around the Earth. This eventually formed the Moon, which began to orbit at a radius of about 60,000 kilometers. The study of the Moon's gravitational field, internal structure, and the reconstruction of its thermal history has revealed the presence of both a solid inner core and an outer metallic core within the Moon. The Moon has a very weak magnetic field, generated by residual magnetism in lunar rocks and the tidal forces acting on its core. The key mystery behind the Moon's gradual drift away from Earth lies in tidal acceleration. This is an effect caused by gravitational interactions in a natural satellite central body system. The primary consequences of this effect are changes in the satellite's orbit and alterations in the central body's rotation about its axis, as observed in the Earth-Moon system. Another consequence is the heating of a planet's interior, which is believed to have had a significant impact on Earth's past. The Moon has been orbiting Earth for the past 4.5 billion years. Due to Earth's greater mass, it exerts a much stronger gravitational force on the Moon than the Moon does on Earth. This means it pulls the Moon towards itself more strongly. This results in tidal forces that cause tides in our oceans. Gravitational attraction between the Moon and Earth is stronger on the side of Earth facing the Moon. This force is strongest in the region closest to the Moon. As a result, the Moon slightly pulls the equatorial regions of Earth towards itself. This significant gravitational pull of the Moon causes high tides in the ocean waters in this region, creating a bulge on the Earth's surface known as the equatorial bulge or tidal bulge. Both sides of the Earth experience this effect, much like how our planet experiences a bulge due to the Moon's gravitational pull. The Moon also experiences a tidal bulge on the side closest to Earth, and this is where we come close to the question of why the Moon is actually moving away from Earth. In reality, there is nothing supernatural about this. It's the nature of both Earth and the Moon to age, and many things change. For example, around 620 million years ago, Earth's days were only 21 hours long, but gradually, days became longer by about 1/500th of a second per century due to the gravitational forces between Earth and the Moon. These forces, along with lunar tides, slow down Earth's rotation. However, due to the conservation of angular momentum for both celestial bodies, the Moon, in turn, begins to rotate faster and move into wider orbits. Will there ever be a moment when our natural satellite disappears into the depths of the universe? Perhaps, but not until about 4.5 billion years from now, when our sun starts to fade and becomes a red giant. However, there's another scenario to consider. We now know that since its formation, the Moon has been gradually moving away from our planet. The rate of this movement has been increasing and is currently about 3.8 centimeters per year. If this continues, you might wonder how the Moon could ever fall to Earth. Believe it or not, some scientists believe this scenario is possible, though fortunately, it won't happen anytime soon. A few years ago, American planetary scientist Jason Barnes stated that the Moon could collide with Earth in about 6.5 billion years. He explained this by suggesting that by that time, Earth's rotational speed would significantly slow down. According to various estimates, this could happen in approximately 50 billion years when celestial bodies reach a mutual spin-orbital resonance. As a result, the moon would not move away, but would be drawn closer to our planet. Interestingly, our sun might play a role in this. Approximately 5 billion years from now, our sun will deplete its hydrogen, which is its source of energy. It will enter a new phase of its evolution, becoming a red giant. The star's luminosity will increase, internal pressure will rise, and its outer shell will expand. Powerful outbursts from the red giant's atmosphere could quickly alter the moon's orbit, causing it to slowly move toward Earth. But will there be a collision? If you're thinking of a head-on collision, that's not the case. When the distance between the moon and Earth decreases to about 18,000 kilometers, the Roche limit, tidal interactions will tear the moon apart into a massive pile of debris. Some of this debris will form a system of rings around Earth. Over time, most of the rings will disintegrate, and the remnants will collide with Earth. In any case, by that time, life on Earth will be impossible, just as it will be on any other planet in the solar system. When the sun transforms into a red giant, the star's atmosphere will expand so much that it could reach the current orbit of Earth. Of course, before this happens, the two planets closest to the sun, Mercury and Venus, will be completely destroyed. Let's exclude the presence of a red giant from this chain of events. In such a case, how would it affect Earth? The disappearance of the moon would have a significant impact. Although the moon's influence on stabilizing the Earth's axis of rotation is somewhat exaggerated, this influence is undeniable. It was previously believed that if the moon disappeared, the Earth's axial rotation would become completely chaotic. This would manifest in unpredictable changes in seasons. The disappearance of the moon would also greatly affect many species of animals and plants, especially those whose life cycles are somehow linked to tides and tidal patterns. Without the moon, there would be no eclipses, and there would be no object capable of partially blocking the sun's disk. It's worth noting that nights would become darker. You might ask, will the moon eventually drift away from Earth? The moon is gradually moving away from Earth, taking some of Earth's rotational energy with it as it rises in its orbit. The moon's gravitational pull is slowing down Earth's rotation, causing Earth to spin more slowly around its axis. Eventually, the moon will reach a geostationary orbit where the satellite's speed over the planet matches Earth's rotation speed. The moon will be in a geostationary orbit, and a phenomenon known as tidal locking will occur. This means that the moon and Earth will always face each other with the same sides. This is a stable state, and it will continue for billions of years. Only in the very distant future, the influence of our sun or some other object might disrupt the mutual rotation of the Earth-Moon pair, and the moon could fall to Earth. No scientist can accurately say what would happen if the moon disappeared. Of course, it could be blown up, move away from the planet, or anything else might occur. The only thing known for sure is that the planet's climate would change and the conditions for life could worsen. After all, our tandem has existed for so many years. But before that happens, a lot of time must pass, so we are unlikely to know the answer to this question. So in general, there's no need to worry, unless people themselves want to accelerate these processes. The sun's rays penetrated reluctantly through the windows of the dwelling. Having just woken up, he walked over to the window, enjoying the planet bathed in sunlight. "Time to go," he mumbled, putting on his spacesuit and locking the door, heading out for his lunar duties. What is this? Where am I, really? He wondered. It felt like the beginning of a fantastic movie. Oh no, what if, in 100 to 200 years or more, people will be living on the moon just like they do on Earth now? After all, there are already many lunar missions being planned, but more on that later. Let's first remember what this celestial body is and why we haven't been going there for sightseeing, considering that humans have already set foot on the moon. Let's start by recalling how human exploration of the moon began. Humanity began studying the moon more than 2,200 years ago, back in the 3rd century BC. Aristarchus, a Greek, made an approximate measurement of the moon's size in the early 17th century. Galileo observed the moon's mountains and craters through his telescope. From the 1950s, the space age began, and the moon became the first celestial body beyond Earth that humans attempted to reach. Since then, more than 100 robotic explorers from over half a dozen countries have sent spacecraft to the moon. 9 manned missions completed round-trip journeys to the moon and back. The moon was first visited by unmanned Soviet spacecraft Lunar 1 and Lunar 2 in 1959. As of April 2019, 7 countries have achieved the first human landing on the moon, which occurred on July 20, 1969, during the Apollo mission in 1969 to 1972. 12 American astronauts walked on the moon and used lunar rovers to travel its surface, expanding their scientific research. The Apollo astronauts brought back 382 kilograms, 842 pounds, of rock and soil for analysis. Then, the United States followed up with 9 NASA Ranger spacecraft, launched between 1961 and 1965, which provided scientists with close-up photographs of the moon's surface. The Ranger missions were bold, one-shot affairs. Each spacecraft was designed to fly to the moon and take as many pictures as possible before crashing onto its surface. By 1965, the imagery from all the Ranger missions, particularly Ranger 9, provided detailed information about lunar terrain and potential landing hazards for future human missions. Each mission after Apollo 11 marked milestones in space travel and lunar exploration. 4 months after the first human moon landing, Apollo 12 achieved a much more precise lunar landing. Apollo 13 narrowly avoided a disaster in April 1970 when onboard oxygen tanks exploded, forcing the crew to abort their planned lunar landing. All 3 astronauts survived. In January 1971, the commander of Apollo 14, Alan Shepard, set a new record for the farthest flight on the moon, 9,000 feet. He even threw a few golf balls into the nearest crater using a homemade 6-iron. Apollo 15, launched in July 1971, was the first of 3 missions capable of longer stays on the moon, spending 3 days on its surface. They managed to collect hundreds of pounds of lunar samples and traveled over 17 miles on the first manned lunar rover. The Soviet Union sent the remotely controlled lunar rover, Lunokhod-1, to the moon in 1970. Apollo 16 in 1972 and Apollo 17 in 1972 were the last 2 manned lunar missions. Meanwhile, the Russian spacecraft Luna 24, launched unmanned in 1976, became the last mission to land on the moon until the next century. The samples collected during these lunar explorations provided a wealth of knowledge about the geology and formation of the moon. After the dramatic achievements of the 1960s and 1970s, major space agencies shifted their focus to other objects for several decades. Currently, we have 3 robotic spacecraft and an upcoming lunar reconnaissance orbiter and dual spacecraft missions planned for the moon. Now let's talk about what's planned for the near future, with the most promising program, in my opinion, being Artemis. NASA introduced the Artemis program in 2019. According to this program, the heavy-lift rocket SLS, Space Launch System, will transport astronauts to the moon by no later than 2024. The program consists of 2 phases. The first phase involves landing American explorers near the South Pole, where deposits of water ice are located. The second phase aims to establish a continuous presence of astronauts on the lunar surface. Russia, through Roscosmos, plans to resume its lunar program in 2021. They intend to test 2 new rockets this year. The Russian lunar program will be implemented in several stages, extending until 2040. The primary goal is to develop all the necessary technologies, such as creating a lunar station's core module and testing the piloted Federation spacecraft. The second stage involves testing means of access to the lunar surface and conducting the first piloted test flights. In the third stage, the construction of a Russian lunar base should be completed, planned between 2030 and 2035, with astronauts spending at least 2 weeks on the moon. China, of course, couldn't be left behind. This country is determined not to fall behind its competitors, aiming to become a space superpower. Last year, it sent the Tianfu spacecraft, which successfully landed on the moon's surface. This news created quite a stir. Currently, China is preparing its Chang'e 5 lunar rover. When it will be launched and the specific stages of the program's implementation are still unknown, but its mission is to collect lunar soil samples weighing up to 2 kilograms for further study. China appears to be positioning itself to win the new lunar race, surpassing the USA and Russia. Since 2013, the Chinese have been developing the Long March 9, a super heavy rocket. Periodically, information emerges from China about a landing module for a crewed spacecraft. Other spacefaring nations also want to join the race, including European countries, India and Japan. India is working independently, while Japan and Europe are collaborating on joint programs. Why does humanity show such interest in this lifeless, rocky desert called the Moon? Today, many companies are highly interested in lunar tourism, while others aim to extract resources from the Moon. A third perspective sees the Moon as a potential new home for humanity. The Israeli team at Space.il, for instance, has a small probe with the primary goal of inspiring young Israelis worldwide. This landing is meant to motivate a new generation of engineers and scientists who will develop technologies for space exploration. Many hope that in the future, countries can use the Moon as a kind of launching pad for further planetary conquest, such as Mars. By utilizing lunar resources, groups of scientists could extract materials for rocket fuel, enabling journeys to planets that were previously out of reach. This is the vision of Robert Bigelow, the founder of Bigelow Aerospace. His company is focused on creating a lunar base and its development. The Moon could also serve as a testing ground for missions to more distant places in the solar system. According to Bigelow, his company might require a significant number of astronauts who will ensure the functionality of these missions, introduce innovations into space equipment, inform the public, and much more. Bigelow hopes this could become a reality within the next 10 years. However, the question arises, can different countries cooperate on the Moon without conflicts? According to Bigelow, our history hardly contains cases of peaceful coexistence. That's why humanity needs to become wiser and resolve all conflicts on Earth. Transferring them to the Moon would require developing an entirely new level of mutual respect in relations. Regarding the exploration of outer space, all states and private organizations will have to agree on and establish common rules to regulate who has the right to claim a specific area of the lunar surface do not exist at present. According to the 1967 UN treaty signed by 128 countries, no one can own a piece of the Moon. What kind of relationship awaits us with the Moon in the future, and will we be able to visit it for recreational purposes? Time will tell. Could the Moon be an artificial object? In today's space journey, we will travel not too far from our planet, almost like a weekend getaway to the Moon. However, we won't be discussing the standard set of information about it. Instead, we'll contemplate the idea. What if the Moon has an artificial origin? Some conspiracy enthusiasts might exclaim, "Finally!" But that's not how astronomers, who observe it closely, see it. We love science because it allows us to test and either confirm or debunk hypotheses. So put on your spacesuits and let's embark on an exploration of the Moon. There are several theories about the Moon's formation, but the most widely accepted one is the collision hypothesis. According to this hypothesis, in the early history of the solar system, a protoplanet about the size of Mars collided with Earth. Some variations of this theory suggest that this protoplanet was named Theia. The collision resulted in lighter materials being ejected into space, forming the Moon, as well as the creation of the asteroid belt. This hypothesis is supported by observations of the Moon's chemical composition, which is nearly identical to Earth's, indicating a common origin. Additionally, the Moon orbits Earth at a relatively close distance, suggesting it formed in proximity to our planet. While the collision hypothesis is widely accepted, it continues to undergo scientific research and debate. The Moon's origin has long intrigued scientists. Back in the 1960s, Soviet researchers Mikhail Vasin and Alexander Sherbakov proposed a hypothesis suggesting that the Moon is too large to be a natural planetary satellite. Its size is roughly 1/3 of Earth's, while satellites of other planets are much smaller in comparison to their hosts. There are also some other intriguing features about the Moon. For example, Only from Earth can we witness a total solar eclipse, where Earth, the Moon, and the Sun are positioned at just the right distances to allow the Moon to completely cover the Sun periodically. If the Moon were either closer or farther from Earth, we would not observe this phenomenon in the same way. It's hard to shake the thought that all of this was created deliberately. But who and why created it? Where did such precision in the orbits of Earth, the Moon, and the Sun come from? They seem elegantly arranged, as if by a cosmic engineer. If our planet were slightly closer or farther from the Sun, we would never see these beautiful celestial phenomena. Not to mention that the Moon directly regulates the tides on our planet, impacting the life cycles of all Earth's creatures, including humans. The analysis of lunar soil collected by rovers has shown that it appears to be magnetized, even though the Moon lacks its own magnetic field. What's intriguing is the suggestion that the Moon may be older not only than Earth, but also than the Sun itself. Some propose that the Moon appeared in our sky relatively recently. Some conspiracy theorists suggest analyzing the legends and myths of various ancient civilizations to find accounts of times when there was no moon in the sky, followed by its sudden appearance. In fact, there are legends of 2 moons, but one supposedly disappeared. Lunar craters have nearly uniform depths, indicating that meteorites that impacted the surface encountered some kind of resistance, likely a metallic shell. On Earth, similar metallic shells are used to make submarine hulls. This suggests that the Moon has a very solid shell. When the Moon's density was measured, it turned out to be surprisingly low, much lower than Earth's. This led to the speculation that the Moon might be hollow inside. Many experiments have supported the idea that there are massive metal masses hidden within the Moon's core. All of this has led scientists to consider the possibility that our Moon is actually an abandoned spacecraft or a discarded extraterrestrial base station. However, there's another theory. This spacecraft is ancient, but still operational. In 1969, when a NASA spacecraft crashed on the Moon, it vibrated like a bell for an hour, emitting seismic activity. This incident puzzled scientists, and they began to wonder why such an event occurred. By all calculations, the answer could be 1, if the Moon is hollow inside. However, natural celestial bodies cannot have such large voids. Either errors were made in the calculations, or Earth's satellite was artificially constructed. Over the next 3 years, leading researchers at NASA tried to find flaws in the initial assessments, but found no faults. The only working theory that emerged was that the Moon might be an artificial creation. Lunar soil brought back to Earth was studied in 6 laboratories, and what astonished scientists was the composition of the Moon's rocks. They contained titanium and minerals with similar characteristics to those on Earth. This composition contributes to the Moon's incredible strength. Additionally, the presence of creep rocks in lunar soil, rich in so-called incompatible elements that accumulate in the liquid phase during magma crystallization, was notable. It also contained heat-producing elements, including radioactive uranium, thorium, and the radioactive isotope potassium-40. All of this further supported the hypothesis of the Moon's artificial origin. Furthermore, it became clear that the Earth's satellite must be hollow inside. There should be vast cavities beneath the solid surface. Otherwise, the vibrations resulting from the relatively weak crash of the NASA satellite would not have been as prolonged and powerful. Astronomers from the USSR and France who became interested in the Moon's origin proposed a hypothesis that it's not just an artificial satellite, but a colossal installation of an unknown civilization. Natural satellites should have much smaller radii than the Moon, according to their calculations. In 2002, NASA's website published findings that supported the assumptions made 20 years earlier, suggesting that the Moon is an exception to the rules. But what about the fragile regolith? For decades, there have been reports of an extremely lightweight and fragile lunar soil. However, there's a hypothesis that this is actually settled cosmic dust, and the real lunar soil is an incredibly robust alloy of titanium and minerals. Hundreds of thousands of years ago, Earth's satellite was a perfectly spherical body, which over millennia has transformed into a cratered celestial object. Speaking of craters, they also emphasize this hypothesis. Their diameters vary from a few meters to several kilometers, yet they all have roughly the same depth. This is unusual because larger meteorites should create wider and deeper craters. This rule only partially applies, mainly to those meteorites that left astroblems with diameters greater than a kilometer, indicating that a colossal impact occurred. Even in these cases, the crater depth reaches only about 8 kilometers, with a diameter of 2,200 kilometers. This once again underscores the fact that the lunar soil is incredibly sturdy, preventing the Earth's satellite from breaking apart upon the impact of such a massive celestial body. In 2009, research conducted by American scientists revealed that the lunar surface consists of two layers of substances: a less durable outer layer, about 6 kilometers thick at the poles, and a more durable layer about 25 kilometers thick, known as the dark armor. In nature, substances can undergo diffusion. In such cases, a transitional layer is created when two substances react and mix. However, on the Moon, there's no such observed transition. It's as if there are two distinct layers with a clear boundary. Unfortunately, modern technology doesn't allow us to determine what lies beneath the dark armor. So, for now, the tinfoil hats can be set aside. Meanwhile, French scientists combined available data and computer modeling to ascertain what lies beneath the lunar surface. To understand the Moon's structure, the composition of Earth and other celestial bodies, astronomers have to rely on data from seismic activity. How acoustic waves created by surface vibrations travel through and reflect off the material inside the planet or moon helps scientists create a detailed map of the object's interior. However, there's a problem when it comes to the Moon. Due to the Apollo missions, we do have seismic activity data, but the resolution is too low to precisely determine the composition of the lunar core. It is assumed that a liquid outer core surrounds the solid inner core, but this hasn't been definitively proven. According to research published in the journal Nature, astronomers from the French National Center for Scientific Research used known facts to create a profile of the Moon's characteristics. These included the extent of its deformation due to gravitational interaction with Earth, variations in distance from Earth, and density. They conducted modeling with various core materials to find a model that matched observational data. They found that the lunar core should closely resemble that of Earth, with an outer liquid layer and a solid inner core. According to their modeling, the outer core has a radius of approximately 362 kilometers, and the inner core is about 258 kilometers. This accounts for about 15% of the Moon's total radius. The inner core, as discovered by the team, also has a density of about 782 kilograms per cubic meter, very close to the density of iron. Thus, scientists were able to confirm earlier hypotheses about a lunar core similar to Earth's. Further exploration of the satellite will help us learn more about its history and the disappearance of magnetic fields. Such a magnetic field is sustained by motion and convection in the core, so what makes up the lunar core is directly related to how and why the magnetic field disappeared. Considering humanity's hope to return to the Moon in the relatively near future, we may have to wait for seismic confirmation of these discoveries. In the meantime, representatives of different countries are debating the rules for exploring the closest planets in the solar system. Ownership of lunar land. Certificates for lunar land parcels are being sold online, and while such purchases are not widespread, they are in demand. Experts continue to debate the legal validity of such private property deals on other planets and their satellites. Outer space, including the Moon and other celestial bodies, is not subject to national appropriation, whether through claims of sovereignty or any other means. This is stated in the second article of the Outer Space Treaty, signed by more than 100 countries worldwide in 1967. However, even if we were to acknowledge that private individuals and companies can own land on the Moon, the question remains: who can rightfully claim such ownership? According to the claims of the Lunar Embassy itself, more than 6 million people have purchased lunar land through them. By 2013, the company had earned about $11 million from these sales, and while more recent data isn't available, it's likely that this sum hasn't significantly increased as the trend for such purchases has waned. Prices for lunar land parcels on the Lunar MBC website range from $25 for approximately 40 acres to $500. As the saying goes, there's no smoke without fire. After comparing data obtained using mini-RF with maps of metal oxide concentrations made with a wide-angle camera LROU, scientists confirmed that larger craters with higher dielectric properties are directly related to the concentration of these metallic minerals. While the first few hundred meters below the silvery lunar surface may lack any precious metals, the deeper you go, the more valuable metals there are. These discoveries bolster NASA's mission. The Laboratory for Restoring Gravity and Internal Affairs, which found a mass of metals 5 times greater than the large island of Hawaii beneath the South Pole Aitken Basin, says these mini-RF data are invaluable. They not only continues to provide data on what might be hiding on the surface of the moon and beneath it, but also sheds light on how it formed and what its true celestial connection with Earth might be. The race to attract wealthy clients into space continues, but the race for mining valuable minerals on the moon is just beginning. The most interesting moons in the solar system. It's hard to imagine our night sky without the moon. Some compare it to a cheese wheel, others see an unassuming face observing nighttime life, while to some, it simply lights the evening path. The moon is the first planet's satellite closest to the sun. Our neighbors Mercury and Venus move through space without having a single satellite, but Mars, on the other hand, can boast of having 2 natural satellites. Beyond that, just imagine, in 2019, astronomers discovered 20 new satellites of Saturn, making it the record holder in the solar system for the number of known satellites with a total of 82. That's some busy traffic. Yet they say space is nothing but emptiness. The other planets in our system also have dozens of satellites each. However, today we would like to find out which of these moons can be called the most interesting, so let's find out. Ganymede. Ganymede is the largest moon in the solar system, and it orbits Jupiter. It even has its magnetic field. Its diameter is 5,268 kilometers, which is 8% larger than that of Mercury. However, its mass is only 45% of Mercury's mass. But among planetary satellites, it's exceptionally large. Ganymede exceeds the moon in mass by 2.2 times. Interestingly, it's quite fitting for its owner, Jupiter. This moon was discovered by Galileo Galilei, and its name was given by another astronomer, Simon Marius, in honor of Ganymede, the cupbearer at the feasts of Zeus. By the way, Marius gave names to some other moons as well. Thanks to him, the names of heroes from ancient mythology became widespread in the newly discovered world of moons. In common language, sometimes satellites are also called moons. Some consider Titan, Saturn's moon, to be the most promising celestial body for colonization, rather than Mars. It has a dense atmosphere, 1/3 denser than Earth's, and it likely has water from which oxygen can be obtained. This atmosphere effectively shields it from cosmic radiation. Moreover, Titan is the only celestial body besides Earth where the existence of liquid on the surface has been proven. The downside is the local atmosphere consists mainly of methane and other inhospitable gases. Also, it's very cold, about minus 180 degrees Celsius. Jupiter's second largest moon, and one of the 4 Galilean moons, is Callisto, the most distant from the planet. It is the 3rd largest moon in the solar system, following Ganymede and Titan. Callisto's diameter is approximately 99% of Mercury's diameter. It was discovered in 1610 by Galileo Galilei, and was named according to the tradition after a character in ancient Greek mythology, Callisto, who was a lover of Zeus. Nevertheless, Callisto is not the most picturesque object in our system. It is known for having the most craters covering almost its entire surface. There is no geological activity on Callisto, so its terrain remains unsmoothed. Io, one of Jupiter's moons, is the most geologically active body in the solar system. It has over 400 active volcanoes on its surface. Some of these volcanoes have eruptions so powerful that they reach heights of 500 kilometers. Io is primarily composed of silicate rock surrounding a molten core of iron or sulfur. Most of its surface consists of plains covered in sulfur or frozen sulfur dioxide. However, on the moon's surface, you can also observe over 100 mountains that have formed from the moon's crust. Some of these peaks are higher than Mount Everest on Earth. The only known moon that rotates in the opposite direction to its planet is Triton, a moon of Neptune. Triton is one of the few geologically active moons in the solar system, and its complex geological history is evidenced by tectonic activity, intricate terrain, and numerous cryovolcanoes. The average surface temperature of Triton is minus 235 degrees Celsius, making it so cold that nitrogen likely settles on its surface as frost or snow. Triton is believed to be the coldest geologically active object in the solar system. Miranda is a moon of Uranus, and it experiences unique seasonal changes. Each pole of this moon is in complete darkness for 42 years, followed by 42 continuous years of illumination. Miranda possesses a highly diverse surface with various features, including fissures, rifts, valleys, craters, ridges, depressions, and terraces. Its surface appears as though it has been slashed, and it contains the deepest canyons in the solar system, several times deeper than Earth's deepest canyons. Charon, the moon of the dwarf planet Pluto, has a diameter of approximately 1,200 kilometers. In 2006, there was a proposal to classify Charon as a planet, which would have made the Pluto-Charon system a double planet. However, the final resolution introduced the concept of a dwarf planet, and Pluto was classified as such, while Charon remained classified as a moon. In July 2015, NASA's New Horizons spacecraft reached Pluto and Charon, marking the first time in history that they were explored. The spacecraft followed a flyby trajectory and captured images of both sides of Pluto, although the images taken before the flyby have lower resolution. From the images, it is clear that Charon is noticeably darker than Pluto, suggesting that these objects significantly differ in composition. While Pluto's surface contains a lot of nitrogen ice, Charon is covered in water ice, and its surface exhibits a more neutral, less reddish color. Saturn's moon Iapetus features a unique mountainous ridge encircling its equator. This ridge reaches heights of 13 kilometers and has a width of 20 kilometers. Interestingly, Iapetus's leading hemisphere is as dark as soot, while its trailing hemisphere shines nearly as brightly as freshly fallen snow. It rivals one of the brightest objects in the solar system, Jupiter's moon Europa. By the way, Iapetus has a similar feature in its far neighbor, Pan, which has an unusual shape resembling a dumpling. This shape is likely due to the accumulation of material from Saturn's rings on Pan's surface. Mimas, another moon of the gas giant Saturn, is of interest to Star Wars fans, as it bears a resemblance to the Death Star from the famous franchise. Mimas has a diameter of about 400 kilometers and is the smallest spherical object in the solar system. In the past, it narrowly escaped being shattered by a large impact crater called Herschel, which had a diameter about 30% of Mimas itself. The cracks left behind by this colossal impact are clearly visible even on the opposite side of the moon. Next in our selection are Mars' two moons, Phobos and Deimos, named after the sons of the ancient Greek god of war, Ares, who is also known as Mars in Roman mythology. So, their names are quite clear. Interestingly, astronomers had been searching for these moons for quite some time before their discovery. It is said that in Jonathan Swift's Gulliver's Travels, written almost 300 years ago, it was mentioned that astronomers from the flying island of Laputa had discovered two of Mars's moons. What's even more interesting is that Deimos gradually increases its orbit radius with each revolution around the planet, while Phobos, on the contrary, decreases its orbit. So in the future, Deimos might escape into space, while Phobos could crash onto Mars, causing unprecedented cataclysms on the planet. However, this won't happen anytime soon. These are the fascinating and unusual moons that orbit the planets in our solar system. It would be wonderful if more exploration missions were sent from our planet to study this variety of moons further. On Saturn's moon Titan, there are both land and seas, as well as 6 elements that are abundant, so scientists believe that there is a high possibility of life on Titan. Let's take a closer look at the possibility of life on Titan. Titan, a moon of Saturn, is huge, second only to Ganymede in size among moons in the solar system. With a radius of about 2,575 kilometers, it is 1.5 times larger than the Moon and about 40% the size of the Earth. Although it can be observed from Earth, it is difficult to observe Titan's interior properly because of its thick atmosphere. Therefore, Titan was a mysterious celestial body shrouded in mystery for a while. However, in 1997, the European Space Agency and NASA launched the Cassini spacecraft to explore Saturn and its moons, and this spacecraft visited Titan. Hundreds of photos and atmospheric composition analysis were sent to Earth, revealing its identity. The image of Titan sent by the Cassini spacecraft was quite ordinary, with mostly wide plains and sand dunes created by the wind in low-lying areas. There were even mountains as high as 3,330 meters. At first glance, these photos looked like hazy days on Earth with dust or fine dust. Clouds were also observed in the sky of Titan. Weather phenomena occurred on Titan similar to those on Earth, with rain falling and lakes forming on the plains, and even seas forming in low-lying areas. Like Earth, liquid circulation also occurs on Titan. With this information, it seems that the speculations of Professor Carl Sagan, who was always right about the possibility of life on Titan, were not true. Or perhaps humans on Earth will one day be able to live on Titan. Because it is located as far as 1.4 billion kilometers away from the Sun, it doesn't receive enough solar heat properly. So as it turns out, the average temperature of Titan is minus 179 degrees Celsius. Titan can be called a supergiant freezer. Normally, if the temperature is minus 179 degrees, all the clothes on this satellite should freeze. Clouds 3 and oceans confirmed through Cassini-5 have a significant discrepancy with what we usually know. The hills on Titan were formed by completely freezing, and the seas on Titan were made up of methane. Also, the clouds were not white clouds gathered by water vapor like Earth, but had a murky appearance. When we only saw Titan in photos, we thought it could be habitable, but it's definitely not a place with a climate like Earth. Even though our environment is like this, scientists' opinions were very positive when Titan was discovered, except for Earth, as it is the only place where liquid is maintained on the surface in a stable way. This is the first celestial body that we confirmed, and there might be life forms here. Also, thanks to the layered structure of Titan, there are winds and rain, making it an optimal place for life. Now let's take a closer look at Titan. Titan has a dense, murky atmosphere. The atmospheric pressure is about 1.45 times that of Earth, and about 98% of the atmosphere is made up of nitrogen with trace amounts of methane. Interestingly, aside from Earth, Titan is the only celestial body in the solar system with nitrogen. Scientists say that Titan's nitrogen-rich atmosphere is very similar to the primitive atmosphere of Earth about 3.8 billion years ago. If we can analyze Titan's atmosphere, we can learn more about the changes in Earth's atmosphere. Currently, nitrogen is the most abundant gas in Earth's atmosphere, accounting for 78%, followed by oxygen at 21% and argon at 0.90%. These atmospheric compositions are present on Earth. However, these ratios have changed slightly over the course of several hundred million to billions of years. Titan's dense nitrogen atmosphere causes a greenhouse effect, which maintains a high temperature despite receiving very little solar radiation. This keeps methane in a liquid and gaseous state. If Titan did not have nitrogen, all of its methane would have frozen, and Titan itself would have become a completely frozen celestial body. Amazingly, the study of Titan has even led to the discovery of some unique molecules that are essential for life formation, such as cyclopropenylidene, which is composed of carbon and 2 hydrogen atoms. This molecule is an important building block for life and also serves as food for other organisms. Although cyclopropenylidene is difficult to pronounce and understand, it is a crucial substance that cannot be overlooked in the formation of life in the universe, and has been observed occasionally in interstellar matter. However, except for Titan, there has been no discovery of such compounds in other celestial bodies, so it's really amazing and remarkable. Cyclopropenylidene, composed of 2 carbon atoms and 2 hydrogen atoms, has been discovered in Titan's atmosphere using the ALMA radio telescope by NASA's research team. The discovery of this molecule, which is difficult to pronounce and has caused quite a stir, is an essential component of the formation of living organisms and can also serve as food for other organisms. Although it has occasionally been observed among interstellar substances in the universe, it has never been found in any other celestial body until now, except for Titan. This is really remarkable, especially considering that it has only been found in two places: Titan, which is similar to the primitive Earth environment, and some other celestial body. Moreover, many benzene compounds have also been detected. These compounds play a role in the formation of complex organic matter. In addition, there are other compounds such as argon and carbon monoxide in the atmosphere of Titan, which is conducive to the formation of organic matter during its evolution. It is an environment where organic matter formed during its evolution is falling like light snow. There is one more fact to note about Titan. It is that 82% of its surface is covered with organic matter. According to Dr. Rosalie Lopez, a NASA scientist, more than 82% of Titan's surface is composed of organic matter that has fallen from its atmosphere and has been transported by winds. This means that Titan's organic matter is very abundant, which suggests the possibility of the existence of living organisms. This is an exciting discovery that raises the possibility of the existence of microbial or other life forms. If such life forms were present, there would be abundant sources of food. Another important fact is that there are oceans on Titan. Prior to this, lakes were discovered on Titan, but now it has been revealed that there are oceans as well. If the liquid in these oceans seeps into the subsurface, it could provide sufficient conditions for the birth of life. While this liquid is not water, Titan is the only celestial body in our solar system, besides Earth, where liquid exists on the surface. Scientists have found that Titan's oceans are deeper than previously thought. In fact, during an investigation of one of Titan's seas, Kraken Mare, the equipment that was used to probe the sea was limited by its technological capabilities and was unable to reach the bottom, which is at least 300 meters deep. This is more than 7 times deeper than the average depth of the West Sea, which is approximately 43 meters. In addition, there are geological activities like volcanic activities in Titan, and if such visual activities occur, an ecosystem ranging from microorganisms that use organic matter around the hot springs as food to predators on top of them may have formed. From the beginning, including Titan, organic matter is very abundant, so if miraculously some organisms were discovered on Titan, an ecosystem of organisms and their mothers could have already formed in Titan's seas. The most important clue is this. Recently, it was found that after hydrogen descends from Titan's atmosphere, it disappears from the surface, according to the data collected by Cassini. Some scientists at JPL are claiming that this may be the result of primitive life breathing in and consuming material on the surface. However, Titan's flowing liquid is methane, so if life is actually emerging and surviving here on Titan, the living organisms of Titan may be based on methane. Scientists are looking at Titan's existence of life with a very positive outlook. NASA has started the Dragonfly project to explore the seas of Titan. They will fly a kind of drone powered by a blue-tone fuel to observe various terrains of Titan. The Dragonfly project is expected to launch in 2026 and arrive near Saturn in 2034. They plan to use a parachute to land on Titan when the weather is favorable, and then switch to flight mode to explore and collect samples. Previously, Genius explorations were mostly conducted using ground vehicles, but this method had limitations in mobility, so the goal is to easily explore multiple locations. I will go crazy with my child's drone to explore. The target distance and time for the exploration are about 2 years, 7 months, and approximately 175 kilometers. This distance is twice the distance traveled by all Mars rovers so far. NASA hasn't made a final decision yet, but they say they could send a 1-ton submarine to Titan. The purpose would be to explore the largest Kraken Mare Sea on Titan, which has a fairly deep depth from the beginning. A submarine would be 10 times better than a drone to explore it. If we explore the liquid methane ocean with a submarine, we could thoroughly examine the ocean floor. What do you think about the possibility of life on Titan, Saturn's moon? Often, the surrounding world appears ordinary and mundane to its inhabitants. However, once you take a closer look at it, everything turns out to be quite different. For a long time, we believed that our solar system was just one of many star systems in the Milky Way. It contains rocky planets as usual and gas giants as well. However, Soon astronomy made significant progress in studying and modeling planetary orbits, and it turned out that our system is extraordinary, not merely because it houses Earth with intelligent beings. It all started with Jupiter. Its orbit deviates significantly from being circular. Its elongation, scientifically known as eccentricity, is 3 times greater than that of Earth. We know that it is challenging to alter the orbit of a celestial body, especially if it has a substantial mass. And the more massive it is, the harder it is to change its orbit. In the early days of the solar system, when young planets were forming from the protoplanetary disk, they had flat, circular orbits. To achieve their current elongation, there must have been some gravitational interaction with another object. Jupiter's mass exceeds that of Earth by 318 times, and all other planets in the solar system by 2.5 times. To stretch its orbit to such an extent, gravitational interactions of colossal scales are needed. But with whom? What planet could be massive enough to influence Jupiter? Uranus and Neptune are also peculiar. According to calculations, they should have taken longer to form in their current positions than the protoplanetary disk could have existed. The only reasonable explanation for this paradox is to assume that they first formed much closer to the Sun and then migrated farther away. But the main mystery in our system is Mars. Also, the rocky planets in general follow a pattern. The farther a planet is from the Sun, the more massive it is. This makes sense because the farther a certain part of the protoplanetary cloud is from the star, the less material from that part of the cloud will be expelled by the star's radiation and solar wind. At first glance, this pattern holds true. Mercury is 15 times lighter than Venus, and Venus is 1.18 times lighter than Earth. But then we have Mars. Here, the regularity breaks. It is 9 times lighter than our planet. Certainly, some issues can be resolved by suggesting that Jupiter's gravity pushed away from Mars some part of the planetesimals, the small bodies from which Earth-type planets were formed. However, calculations show that a planet comparable in size to Earth should have formed in Mars' place, and the issue is not with the calculations or the theory. Mars lies within the habitable zone of the solar system. If it had an atmosphere comparable to Earth's, it would retain enough warmth to have a climate similar to Earth's arid regions. But in practice, its atmosphere is 150 times thinner than ours, and its gravity is too weak to hold a denser envelope. This is a fact. Clearly, if Mars were 5 to 9 times more massive than it is now, it would be inhabitable. Observations of other planetary systems show that planets the size of Earth, Venus, Mars, and Mercury are a significant rarity. Rocky worlds usually have masses noticeably larger than Earth's, earning them the name super-Earths. So, are all the planets in our terrestrial group anomalies? Astronomers Michael Brown and Konstantin Batygin, supported by most global scientists, believe that a super-Earth exists in our solar system as well. However, it is incredibly distant from the Sun, hundreds of times farther from Earth, and tens of times farther from Neptune. In other systems, planetary migration, moving closer or farther from their stars, is, surprisingly, a common occurrence. A whole class of planets called hot Jupiters exists only due to their migrations toward their stars, but our Sun has none. Gas giants cannot form close to a star because radiation blows away light elements to more distant regions. However, after formation, a gas giant might lose orbital stability and collide with planetesimals that gradually slow down its rotation around the star. As the planet's rotational speed decreases, it carves out concentric circles around its star, while its gravity ejects objects encountered along the way from the system. As a result, hot Jupiters often leave their stars without terrestrial planets and get so close to them that they heat up to thousands of degrees. This scenario paints a clear picture. Our system might have been quite different at the beginning. The giant planets didn't necessarily originate where they are now. Astronomers have constructed several detailed mathematical models of the movement of bodies in the solar system and made an unexpected discovery. From the perspective of celestial mechanics, the original formation region of Jupiter, the one that would be compatible with its current eccentricity and orbital position, is located at a distance of only 3.5 astronomical units from the Sun, meaning 3.5 times farther than the current distance between Earth and the star. However, Jupiter is currently at an average distance of 5.2 astronomical units from the Sun, which is 250 million kilometers farther away. So, how did it end up there? Here, computer modeling came in handy. Collisions with planetesimals slowed down Jupiter's rotation around the Sun, causing the planet to move on its orbit more slowly and, consequently, start to approach the Sun. On its way inward, Jupiter's gravity caught up with Saturn. Terrestrial planets form more slowly than gas giants and complete their formation after them. Therefore, Earth and Mars were somewhat lucky. If they existed at that time, they would have been in danger. Jupiter stopped at a mere 1.5 astronomical units from the Sun, slightly closer than Mars. The formed planets would have received too strong a gravitational impulse from Jupiter, and their orbits would have been too unstable. There was a high chance they would be ejected from the system. Nevertheless, Jupiter's migration caused significant difficulties for the unborn rocky planets. Its gravity did its job. Gas and dust from this part of the protoplanetary disk were literally absorbed by Jupiter, and some of the planetesimals were thrown out of the system. The region where Mars formed was so depleted of material that it ended up significantly smaller than Earth. But then why did Jupiter not stay at 1.5 astronomical units from the Sun and instead turn back? The explanation is straightforward. Saturn, following Jupiter, eventually entered into an orbital resonance with it. This means that Saturn's period of 2 orbits around the Sun became equal to 3 rotations of Jupiter, a 3-4-2 resonance. The presence of orbital resonance means that the bodies regularly align with each other. The gravitational interaction between them sharply increases, and their orbits receive significant corrections. The interaction with Saturn pulled Jupiter back just in time. Imagine what would have happened if the largest gas giant didn't stop at 1.5 astronomical units, but reached 1 unit, that is, Earth's orbit. Perhaps there would be no one to ask questions in that case. Earth would have been a small planet like Mars, and fortunately, Jupiter's walk would not have left much material for its formation. If life existed on it, it would hardly be as developed as it is today. Some believe that Jupiter is Earth's protector, safeguarding the planet from asteroid impacts. Well, then Saturn becomes Earth's savior. Such a journey of Jupiter couldn't help but influence Uranus and Neptune. Initially, they were not farther than 17 astronomical units from the Sun. The migrations of Jupiter and Saturn eventually threw them onto more distant orbits. They remain there today. Uranus at an average distance of 19 astronomical units from the Sun, and Neptune at 30. But what about the presence of super-Earths in the solar system? This is the most massive class of planets, but there is not a single one in our system. They form faster than the smaller bodies of the terrestrial group, so by the beginning of Jupiter's migration, they could have already existed in our system. In this case, an unfortunate fate awaited them. They were destined to be destroyed by falling onto the Sun. The remaining material of the protoplanetary disk in the regions where rocky planets formed in the solar system was too little to form a second generation of super-Earths. All it managed to do was to form 4 planets, with Earth accounting for approximately half of the total mass. However, things are not as straightforward as they seem. Practically any computer modeling of early migrations in the solar system indicates that its current configuration is unlikely. According to the most plausible scenario, the planets should have been on different orbits with slightly different eccentricities. Astronomers pondered this problem for a long time until they tried introducing additional planets into the modeling. It turned out that with the presence of 5 giant planets in the early solar system, instead of 4 as it is today, the probability of the system forming in its current state increases significantly. Almost certainly, some 4.6 billion years ago, there were indeed 5 such planets, and the 5th one was an ice giant, similar to Uranus or Neptune. Moreover, astronomers Batygin and Brown, who proposed the hypothesis of the 9th planet orbiting hundreds of astronomical units from the Sun, note that it is most likely a large object, or one of them, that was once ejected by Jupiter's great journey there and back. So, practically the entire architecture of the solar system was determined by events that occurred before Earth even existed. In the place where Mercury, Venus, our planet, and Mars are now, There might have been super-Earths, possibly more than one. At that time, there were 5 giant planets, not 4. The chaotic migration of Jupiter and Saturn destroyed all ancient super-Earths, casting them into the Sun, and at the same time expelled the current 9th planet of the solar system. Jupiter and Saturn themselves moved away from the Sun, and Uranus and Neptune moved even farther. It turns out that the migration of giant planets is the key mechanism that governs the scenario of planetary system evolution. Those systems with hot Jupiters may be devoid of terrestrial planets and chances of habitability. Their giant planets are so hot because their migration ended close to the star. They did not have their own Saturn to reverse their orbits. The constant presence of giant planets on orbits close to the star makes the presence of smaller rocky planets within the habitable zone even less likely. However, there are systems where giant planet migrations did not occur at all. In such cases, super-Earths are formed on orbits close to the star. The most well-known system with such a setup is TRAPPIST-1, located 40 light-years away from Earth. It is still unknown how habitable they are, but if they are, there might be more than one habitable planet in such systems, sometimes even more than 2. Whether this is true or not, we may find out in the coming years, thanks to the James Webb Space Telescope, which will soon begin its work. Before the era of mass exoplanet discoveries, scientists widely believed that the solar system was a favorable place for the formation of Earth-like planets and life. However, today, knowing about the Great Migration of Jupiter, this hypothesis seems less plausible. Earth miraculously avoided destruction and was not ejected into interstellar space. It appears that the birth of a habitable home in our system was an extraordinarily challenging process, and the number of planets suitable for habitation here is noticeably lower than what one might expect in more stable systems. In the year 2020, we have images of black holes, breathtaking panoramas of the Milky Way, detailed snapshots of distant galaxies, and the stunning James Webb Telescope is getting ready for launch. However, 30 to 35 years ago, everything was so different that such news would likely have shocked engineers and scientists. If we had the opportunity to call a scientist directly in the year 1985 and ask a couple of interesting questions, like the existence of planets around other stars, they would probably say that it's likely, but not certain. Now, it's not 1985 anymore, and thanks to new methods and modern technology, today we have thousands of stars in our own galaxy that have their own solar systems. We have discovered planets of various sizes, characteristics, and masses at various distances from their stars. We have planets even larger than Jupiter that orbit stars in less than 48 hours, and NASA's Kepler mission has made a huge contribution to the search for such planets. It's no longer breaking news that Earth-like planets are being discovered. But let's reason more simply. As each of us has a specific idea of what intelligent life is, and each of us has an idea of the conditions under which this life can exist. Let's imagine a simple analogy: intelligent life in the universe and an ordinary tree. If I ask you whether a tree can grow inside an iron box, or whether it can exist there, you would accurately say no, because you understand that a tree requires certain ingredients, such as soil, fresh air, sunlight, and some nutrients. In fact, the logic is such that we just need to find the same things that exist on Earth, and then we will surely find life. This is how we think now. But consider the fact that you are not Mickey, defining the concept of life only like the one on our Earth, because you haven't seen any other life, heard nothing about it, and are unlikely to hear about it in the near future, and maybe never. So, if we set ourselves the question of searching or pondering whether intelligent life exists in the universe, it's important to understand correctly what form or type of life we want to find. It could be similar to us or something entirely different. Of course, the simplest ways to answer such a question are to apply mathematics, probability theory, and real observations. But in that case, once again, we will be looking for life solely similar to ours. Remember that tree I mentioned. The key point is that we know what it looks like and what conditions it needs. Therefore, we can easily predict where a tree can grow and where it's extremely impossible. If you want a simple answer to the question of whether life exists somewhere in the universe besides us, I will say that it's 100% likely, given what we consider as life. I know this is my personal opinion, but I will try to explain why I'm confident about it. I present to you 10 amazing places in the universe with a full potential for the formation of life. It's not a secret that soon after the formation of our planet, life appeared on Earth and is progressing today. Of course, it's possible that earthly life didn't originate on Earth, but came from somewhere else through natural cosmic processes. And in this conversation, it doesn't matter whether it originated here or somewhere else. What's important is that the basic ingredients for life exist everywhere we look. For example, consider a dozen places where these ingredients are most frequently found. First, there's gas ejected from young objects, like the Herbig-Haro objects, which contain various organic molecules. Another example is protoplanetary disks, where there's a vast diversity of complex compounds and organic molecules. For instance, there's the protoplanetary disk around the young star, HL Tauri, photographed by ALMA. The gap in the disk indicates the presence of new planets, and spectroscopic measurements reveal a large variety of carbon-containing compounds, which are essential for life. Even on Pluto, there's thallium and methane, and a rich organic haze. Even in the images from the New Horizons mission, atmospheric hazes are clearly visible and measured for the content of several carbon-containing compounds. Nebulae illuminated by a bright young star are rich in numerous complex carbon compounds, are reflective nebulae for containing a wide variety of complex organic molecules. Reflective nebulae are common sources of raw materials for life. By the way, inside meteorites, there are numerous amino acids and proteins, some of which are not found in nature on Earth. For example, the Murchison meteorite that fell in Australia in the 20th century. The fact that there are more than 80 unique types of amino acids suggests that basic ingredients for life, or even life itself, could have formed differently somewhere else in the universe, perhaps even on a planet that is not orbiting a sun-like star. The gas in the galactic center includes vital compounds. Idol's Pharma is responsible for the recognizable aroma of raspberries, though Russian scientists don't acknowledge this. For example, the wave image of the galactic center shows us stars and gas, with a tremendous amount of material, including heavy elements and organic compounds, which are essential precursors for life. And this is the molecular cloud of Taurus, where new stars are formed. It contains dozens of organic substances, including carbon chains. For example, in the image, the brighter areas in red have the highest density and active star formation, while the blue areas correspond to cooler, less dense regions. However, organic molecules are found in both places. Planetary nebulae formed by the death of sun-like stars contain more than 20 molecular species, including fullerenes. These are abundant on Earth. Interestingly, fullerenes and complex organic compounds can form rapidly and survive to a significant extent during the evolution of any star. Nitrogen, hydrogen, and oxygen are strongly highlighted in this planetary nebula. Different colors clearly indicate the locations of various elements, which are separated from each other. Complex molecules, including fullerenes containing 60 carbon atoms each, have been detected in these planetary nebulae. And you don't have to go far. Sedimentary rocks on Mars contain rich organic compounds, some of which are over 3 billion years old. For example, the American NASA rover on Mars discovered ancient organic molecules embedded in sedimentary rock deposits that have existed for billions of years. They contain carbon and sulfur and could be associated with life beyond Earth. Over the past decades, our knowledge of the existence of planets around other stars has grown to incredible numbers. The number of known exoplanets has changed from a few dozen to more than 1,000 officially confirmed objects. Therefore, now we are confident that exoplanets can come in various sizes, be at different distances around all types of stars, have different masses and characteristics, and these are real data. It's not surprising that against the backdrop of such acquired knowledge, various questions arise in our minds, seemingly logical at first glance. For instance, when will we find the first inhabited planet beyond the solar system? Or what does habitability on a planet actually mean? Do planets exist that closely resemble our home, Earth? All this is done in order to understand where else life might exist. However, the thing is, the more we learn, the more we realize that being interested in and searching for a planet similar to ours with the presence of life is very inappropriate. This is because the universe is incredibly diverse, and places with the presence of life might not be anything like Earth. Perhaps these conditions could be even better or completely different from what we can imagine. We'll talk about why the assumption that a planet similar to Earth is a requirement for the existence of life is misleading. Having only one successful example, the planet we inhabit, leads to this kind of misconception. If we look at our solar system with all its planets and moons surrounding us, it becomes obvious that Earth is something unique. Only we know why we consider it special. Maybe it's because Earth is the known world where life originated, was sustained, developed, and flourished. It transformed the biosphere and eventually became complex, diverse, intelligent, and technologically advanced. Scientists are looking for conditions that resemble those Earth has experienced and continues to experience. They assume that a potentially habitable planet with life must be similar to Earth. But this is where they make a crucial mistake, because these assumptions imply that the conditions our Earth has faced are the most favorable for the desired outcome of life. However, as we learn more about the universe and the solar system, we have solid grounds to challenge such an assumption. There are 5 key points we need to consider. The first thing that comes to mind is a planet the size of Earth. After all, it seems like the ideal size for life. If we're too large, we might be enveloped in a massive hydrogen or helium envelope, like Neptune or Uranus. And if we're too small, we might struggle to maintain our atmosphere, like Mars or Mercury. Hence, the conclusion is that Earth's size is the way to life, right? Saturn's moon Titan is smaller than Mars, yet it maintains a denser atmosphere than even Earth. Moons like Europa, a large watery moon of Jupiter, might have ideal conditions for subaquatic oceanic life. Isn't it paradoxical and intriguing? These typical examples are right here in our very own solar system, yet they don't remind us that the potential for life exists in many worlds of vastly different sizes. The size of Earth is not a special prerequisite for life to form. The second point worth mentioning is the so-called habitable zone. If we have a planet the size of Earth with an atmosphere, we need to place it in a favorable location around its parent star to have the necessary temperature for life to initiate. This also seems logical. However, the thing is, a planet much farther from its star can have a denser atmosphere, leading to moderate conditions. A planet with a lower albedo or specific cloud cover properties might be closer to its parent star and still have moderate conditions. Hot planets could thrive in their upper atmospheric layers, while cooler planets could harbor life beneath ice. The habitable zone is a 5th-place starting point, and science has progressed to a point where this simplistic definition is no longer useful. The third point is the ability of a sun-like star. The majority of stars in the universe are red dwarfs, low-mass stars that burn slowly and steadily, in contrast to only about 20% of stars that share the fate of the sun, burning for billions of years before becoming red giants and ending as planetary nebulae. Although red dwarfs mostly have a low mass and undergo very slow nuclear reactions, emitting little light, many planets orbiting them are locked by tidal forces. However, this doesn't mean these conditions impede the formation of life. There is a risk of cutting off unnecessary possibilities by limiting ourselves to our primary assumption. While it's more likely that life in red dwarf systems may be challenging, until we truly start conducting a census of the universe's population, measuring the atmospheric properties of all available planets, we cannot make a comprehensive conclusion that life in these systems doesn't exist at all. The fourth point is that life regulates its own biosphere. This is another key question for which we don't have an exhaustive answer. Can a planet, initially uninhabited and considering only physical and chemical processes, transform and remain habitable during the early stages of simple life? We know Earth has many feedback mechanisms, and we also know that significant external changes might result in only minor changes within our biosphere. Does having simple, early forms of life hold the key to the development of stable, long-lasting life on a planet? After all, the conditions for its origin are more realistic and favorable. If this is the case, we cannot significantly understand what makes a planet potentially suitable for life until we gain a more complete understanding of this matter. The fifth point is the significance of heavy elements. The very first generation of stars consisted mostly of hydrogen and helium. In our solar system, about 2% of the total mass of all objects consists of heavier elements such as oxygen, carbon, nitrogen, and other essential life elements. Stars with a sufficient amount of heavy elements cannot form rocky planets, nor the simple molecules necessary for life. However, where do we draw this line? Can a solar system made up of half heavy elements be sufficient for life to form? And what if the percentage is 10, or even just 1? Or perhaps it could be as high as 500% in the opposite direction. Therefore, regardless of a specific threshold, we lack a clear understanding of whether we are a rarity in the universe or a typical outcome of probability theory. These are just some of the open questions that hinder our comprehension of a planet similar to Earth. An intriguing fact is that the universe plays with numbers. Consider our observations, for example, within the Milky Way. There are approximately 10 billion Earth-sized planets orbiting within the habitable zone of stars similar to our Sun in terms of temperature and mass. A significant portion of different systems have a comparable concentration of heavy elements to our solar system, indicating that a vast number of exoplanets could potentially be candidates for Earth-like conditions. However, there are also numerous exoplanets of a different type that do not meet these criteria. Such planets are far more abundant than those we naively describe as being similar to our own. The quest for Earth-like planets may lead us to overlook many planets in the galaxy where life may have already originated and begun to thrive. In order to discover something, a more unbiased approach would be to observe everything within our capability. Of course, it's easy to argue that Earth possesses all the conditions for life, which should at least allow us to consider the possibility that planets with similar conditions could also harbor life. So let's start by acknowledging the imperfections in our search for life on exoplanets. It's this kind of thinking that ensures we will obtain biased results in any search we conduct. But if, before the search even begins, we simply decide that life cannot exist around red dwarfs, that exoplanets or moons of incorrect sizes or at incorrect distances from their stars will never form life, or that stars with insufficient heavy elements cannot support life-bearing planets, we risk not only overlooking numerous cases of life in the universe, but also the overwhelming majority of habitable planets. The thing is, nearly 80% of the stars in the galaxy are low-mass stars, and there may well be more worlds the size of Mars or Liverpool, smaller than Earth, orbiting these stars than Earth-sized worlds. There's probably a multitude of atmospheric conditions that can permit life at various orbital distances. There might even be more exomoons of significant size around gas-rich massive exoplanets than Earth-sized exoplanets. So how tempting it is to assume that if we have one successful example like Earth, we should seek examples that mimic that known success. However, this is an incorrect scientific approach. The correct approach is to seek as many plausible worlds as possible that could include these conditions, not limiting ourselves to only Earth-like conditions. It's entirely possible that most planets with conditions similar to Earth's are actually inhospitable to life. Meanwhile, many planets with conditions different from ours may be even more suitable for life. Until precise studies reveal the answer, presuming that Earth 2.0 has a precise scientific basis is speculative at best. The story of how the universe became what we see today, from the Big Bang to the vast space filled with galaxies, stars, planets, and life, unites us all. From the perspective of inhabitants of planet Earth, 2/3 of cosmic history passed before the appearance of the Sun and Earth. However, life emerged on our world as far back as we can peer into the past through measurements. It may have appeared even 4.4 billion years ago. This makes us wonder, did life arise in the universe earlier than on our planet? How long ago might it have emerged? To be more precise, how soon after the Big Bang could enough heavy elements accumulate to form planets and possibly life? The answer to this question takes us further into the past than we could ever imagine. Graphite deposits have been discovered in zirconium, which is the oldest evidence of carbon-based life on Earth. The amount of carbon-12 found in these deposits dates the emergence of life on Earth to over 4 billion years ago. Of course, we cannot travel back to the very beginning of the universe, because after the Big Bang, there were not only no stars or galaxies, there were not even any atoms. Everything takes time to come into existence, and the universe, after giving birth to matter and antimatter, started from a fairly homogeneous state. The densest regions comprised only a small fraction, possibly as small as 0.3%, denser than the average. This means it would take an enormous amount of time for gravitational collapse to work on creating, for example, planets that are much denser than the average density of the universe. Yet, the universe had enough time for all of this to come into existence. If we look at the standard timeline of the universe's history, Earth appeared only after 9.2 billion years after the Big Bang, but many of the steps necessary for creating a world like ours happened very early on, just after 1 second. Antimatter annihilated with the majority of matter, leaving a small amount of protons, neutrons, and electrons. A sea of neutrinos formed, and after about 3 to 4 minutes, protons and neutrons combined to form neutral atomic nuclei, but most of these were isotopes of hydrogen and helium. Only when the universe cooled down to a certain temperature, which took approximately 380,000 years, did electrons join these nuclei, forming neutral atoms. However, even with these fundamental ingredients, life and rocky planets were still impossible because cooling the universe meant that atomic nuclei formed, followed by neutral atoms. Yet, practically all of these atoms were hydrogen and helium. Only much later did the heavy elements necessary for the formation of rocky planets and life begin to form. But gravitational collapse is a reality. Given enough time, it will change the face of the universe. At first, it progresses very slowly, but it gains momentum as regions of space become denser. The denser the region becomes, the better it is at attracting more and more matter, and the areas that start with the highest density grow faster than others. Our simulations show that the very first stars should have formed approximately 50 to 100 years after the Big Bang. These stars should have consisted solely of hydrogen and helium and could grow to quite large masses, hundreds or even thousands of times the mass of the Sun. When such a massive star forms, it dies within 1 to 2 million years, but in the moment of its death, something remarkable happens, all thanks to its life. All stars synthesize helium from hydrogen in their cores, but the most massive ones not only synthesize carbon from helium, they also progress to oxygen, neon, magnesium, silicon, sulfur, and so on, following the periodic table of elements until they reach iron, nickel, and cobalt. After this, there's nowhere else to go, and the core collapses. This triggers a supernova explosion. These explosions eject a vast amount of heavy elements into the universe, giving rise to new generations of stars and enriching the interstellar space. The increase in the proportion of heavy elements signifies an increase in the number of rocky planets with high density and the quantity of elements necessary for life as we know it. We don't need the average stellar system in the universe to resemble our solar system. We only need a few generations of stars to live and die in the densest regions of space to replicate conditions suitable for the emergence of rocky planets and organic molecules. For instance, in the remnants of a supernova, there exists a slowly rotating neutron star, formerly a massive star that reached the end of its life. Although supernovae can send the synthesized heavy elements back into the universe, it's the subsequent mergers of neutron stars that create most of the heaviest elements. By the time the universe reaches just 1 billion years old, the most distant objects are abundant in heavy elements, as confirmed by our measurements. There is a significant amount of carbon, as much as in our solar system, and other heavy elements accumulate even faster than carbon. It may take more time to achieve a high concentration because carbon primarily emerges in stars that do not become supernovae themselves. However, carbon is not essential for rocky planets, and other heavy elements also start to accumulate more rapidly. Possibly within several 100 million years after the ignition of the first stars, around 300 to 500 million years after the Big Bang, the most enriched stars have already formed rocky planets. This is seen in the protoplanetary disks around young stars. Gaps in these disks indicate the presence of new planets. As soon as the disk has a sufficient amount of heavy elements, rocky planets can emerge within it. If carbon were not essential for life, similar processes could begin in different regions of the cosmos. However, for life similar to ours, carbon is crucial, which means that the appearance of life may need to wait much longer. Even though carbon atoms will appear in the mix, it will take approximately 1.5 billion years for there to be enough of it. This period is before the universe reaches 10% of its current age. However, it's not just the 5% required for the formation of rocky planets. It's interesting to consider that the universe has formed planets and all necessary ingredients in the right quantities for life to emerge, except for carbon. To create a sufficient amount of this essential ingredient for life, we must wait until the most massive sun-like stars live and die. You see the remnants of supernovae on the left and a planetary nebula on the right. Both of these mechanisms allow stars to return burnt heavy elements to interstellar space, utilizing them for the emergence of stars and planets in the next generation. Sun-like stars, after their death, leave behind planetary nebulae, which are the primary source of carbon in the universe. It takes more time for the production of carbon because stars that give rise to planetary nebulae have longer lifespans than those that perish in supernova. Extrapolating that back into the past, the most advanced forms of life that appeared on Earth in different epochs suggest an interesting exercise. It turns out that the increase in genome complexity follows a certain trend. If we go back to individual paired bases, the time frame suggests something more like 9 to 10 billion years, rather than the 12 to 13 billion years ago the Earth formed. This indicates that life could have emerged a billion years ago. However, in our cosmic region, it took several additional billion years to initiate. On this semi-logarithmic graph, the complexity of organisms, measured by the length of non-redundant DNA relative to the functionally non-redundant DNA, with respect to gene readability through paired nucleotides, linearly increases over time. We do not know this at the current moment. We do not know where the line between life and non-life is drawn. We also do not know if earthly life began here before other formed planets, or somewhere deep in interstellar space without any planets at all. Many amino acids not found in nature have been discovered in the Murchison meteorite, which fell to Earth in Australia in 1969. The fact that over 80 unique types of amino acids exist in a simple cosmic rock suggests that the ingredients for life, or even life itself, might have emerged through interactions on planets. It's intriguing. The elementary ingredients necessary for life appeared shortly after the formation of the first stars, and the most important ingredient is carbon. As the fourth most abundant element in the universe, carbon is the last ingredient to reach the necessary quantity for rocky planets. In some places, rocky planets appeared much earlier than life could have emerged, perhaps as soon as 500 million years after the Big Bang, or even earlier. However, once we have enough carbon, all the necessary steps for the emergence of organic molecules and the initiation of the direction towards life become inevitable. Whatever life processes led to the emergence of humanity, they might have begun when the universe was 10 times smaller than it is now. We can be certain that in our solar system, we are alone. The maximum possibility is the existence of some microbes. These would not be complex multicellular organisms. But where are the intelligent beings? If intelligent beings truly exist in the universe, their location is at least light years away from us. Two independent intelligent civilizations could coexist, excluding interstellar travel. If they followed a similar path as our life, the question arises, where are they? Perhaps we should start with the fact that to emerge, life must go through several stages, yet the ingredients for it are literally everywhere. Even if we limit ourselves to life chemically similar to ours, the universe is teeming with possibilities. Molecules capable of binding, including organic ones, are present both on planets and in space. This is the Omega Nebula, or the Messier 17 mission, an intensely active star-forming region, which explains its dusty and vivid appearance. Stars formed at different stages of cosmic evolution have different proportions of heavy elements. Although Earth formed over 9 billion years after the Big Bang, the universe didn't necessarily have to wait that long. Therefore, we'll categorize stars into 3 population types. The first population type includes Sun-like stars, which consist of 1 to 2% heavier elements than hydrogen and helium. They are composed of processed material, and their planetary systems have gas giants and rocky planets suitable for life. The second population type consists of older, ancient stars with only 0.1% of the heavy elements found in the Sun. Most of their worlds are gaseous and rarefied. They are too primitive and contain too few heavy elements for life to emerge. The third population type includes the earliest stars in the universe, which should be almost entirely free of heavy elements. The study of the earliest galaxies indicates that they are mainly composed of stars from the second population type. However, closer to us, there is a mix of young and old stars, rich and poor in metals. In star distances, the scale is accurate in this illustration, but if the picture were to scale, even the largest stars would be smaller than 1/1,000,000th of a pixel. One of the most important lessons for astronomers came from the Kepler mission when examining the Kepler 4444 system. This first population type star has planets, but they are much older than our Earth. Our planet is only 4.5 billion years old, while the Kepler 444 system is 11.2 billion years old. This means the universe could have formed Earth-like worlds very early, at least 7 billion years before Earth appeared. Considering this possibility and the fact that regions like the center of our galaxy got enriched with metals faster and more significantly than our surroundings, it's quite possible that there are places in the universe, maybe even in our Milky Way, more conducive to the emergence of intelligent life than the Sun-Earth system. Given all that we know about the positioning of stars well suited for the birth of life, let's consider 5 main possibilities. This is the imagination of an artist regarding the TRAPPIST system, with its planets reflecting light from their surfaces. The potential presence of water on each of these worlds is depicted through seas, ponds, and vapor. However, it's unknown if any of these worlds have an atmosphere or if their parent star blew it away. One thing is clear. Potentially habitable worlds are located close to each other at a distance of only 1 million kilometers. In the early days of the solar system, it's likely that Venus, Earth, and Mars, and perhaps even Theia, a hypothetical planet that collided with Earth, had conditions equally suitable for life. Their atmospheres were filled with life-building ingredients, and there was liquid water on their surfaces. Venus and Mars at distances close to Earth's mark, a trajectory that spanned tens of millions of kilometers. However, around a Class M star, a red dwarf, planets could be separated by distances much smaller, as seen in systems like TRAPPIST-1. Potential habitable worlds could be as close as 1 million kilometers apart. Twin moons or planets orbiting a giant world, or a binary planet, could be even closer to each other. If life successfully emerged under certain conditions, why not have it arise twice, almost in the same place? This is a globular cluster, Omega Centauri captured using a powerful telescope. Globular clusters are massive collections of hundreds of thousands of stars, forming a spherical shape with a diameter of a few tens of light years. In the outer edges, the typical star-to-star distance is about a light year, but in the denser inner regions of these star clusters, stars can be as close as the Sun and the Kuiper Belt. Orbits in these star systems must remain stable, even in such crowded surroundings. Considering what we know about globular clusters, which appeared much earlier than the Kepler 4444 system, there should be promising candidates for life and habitability within a few hundred astronomical units. Although this distance changes over time due to star motion, You could call this an incredibly close encounter of two civilizations. This high-resolution image operates very close to the infrared range. Such pictures allowed us to discover 3 superstar clusters in the galactic center. Since long-wave light near infrared penetrates the dense dust between Earth and the galactic center, we could observe these superstar clusters. This cluster is from the central parsec, and all stars in these clusters, as well as the galactic center, are quite young. The closer you get to the galactic center, the denser the stars are. In a few light years from the center, star density is extremely high, much greater than the center of a globular cluster. In a sense, the galactic center is an even denser environment with massive black holes and extremely massive stars and clusters forming. While globular clusters lack these, there is a problem with those stars in the sense that we see them in the Milky Way's core. They are relatively young, possibly due to high variability in their local environment. Stars rarely survive there for even 1 billion years, despite the high density. In this area, stars come in different sizes, colors, and masses, including many bright blue stars, which are dozens or even hundreds of times more massive than the Sun. This is evident in the scattered star cluster NGC 3766. So, let's consider the existence of a civilization in a densely packed star cluster, or a spiral arm. Spiral arms are rich in unusual regions of the galaxy, where young stars are more likely to form from these epochs. Star clusters often contain thousands of stars within a region just a few light years in size. However, stars don't remain in such a configuration for very long. A typical open star cluster disperses in just a few million years, and only a small fraction of them survive for billions of years. Stars constantly enter and exit spiral arms, including our Sun. In summary, while the typical distances between stars within a cluster may be around 1 light year, they are unlikely candidates as the cradle of life. This logarithmic diagram displays distances, showing the Voyager spacecraft, our solar system, and the nearest star. So, let's consider the latest idea that everything is distributed in interstellar space. In other cases, stars end up in the same situation we observe, distances between them being on the order of a few light years. Approaching the center of the galaxy, we can reduce this distance to what is encountered in open clusters, approximately 1 light year. But if we get too close, we face the problems we see in the galactic center: mergers, interactions, and other catastrophic events that are more likely to interfere. To maintain a stable environment, we can reduce the distance, but the typical interstellar space is not suitable for this. If we adjust for close encounters, the best approach would be to wait until another star passes close to the initial one. With a typical star, this happens approximately once every million years. This graph represents the probability of a star passing at a specific distance from the Sun, with both axes being logarithmic. While we don't expect intelligent extraterrestrial life to be a frequent phenomenon in the universe, as common as planets and stars, every world that meets the necessary conditions represents a chance. Each time you get a chance, you gain an opportunity for success, with a finite probability. Each of these possibilities may turn out to be reality, but until we venture there and see what is there and what isn't, it is essential to objectively assess what kind of extraterrestrial intelligence the universe may provide us. The truth is somewhere out there, but it's important to understand that if we were extremely lucky, it could be much closer than we dare to imagine today.